don't know. It'll be
There probably is like 2 pepperonis and 2 cheeses.
Oh, yeah. 叫什么馅儿？什么？就是看到你们这个是吃死了，吃死的东西。哦，只有去一个潘多拉里面。这怎么吃的？都好像吃死。
质量应该是一样。
我就是那个这个四川刚才的，它这个这玩意儿就是用来四川。哦，酸质。
There's some plates. Oh.
then is cog.
Mm. Hi. Should I use my own speaker or yours speaker?
You can use yours.
My own.
Yeah,
Okay.
I'm gonna make you. Once I start the recording, I'll go ahead and make you the host,
Mm-hmm.
just in case I have to step out or anything like that.
Mm-hmm. I record.
Yeah, we'll record it.
Okay, thank you. So can you see my screen in Zoom?
I can see it.
Okay,
I can see the
thank
trees.
Okay.
Sure, yeah. More chairs. Maybe two, three more. We'll figure it out. Kind of hard to gauge attendance because all the Duke ones tend to get reasonable attendance, but a lot of the ones at the other schools are getting smaller attendance, so. Just for that. We'll start at 1:05, like 5 minutes, just let people join.
Sure,
the
sure.
Zoom.
No. I think they can help us.
Okay, guys. I hope you can hear me. Thank you so much for attending this Athena student seminar series. This week, we have my postdoc, Dr. Cong Guo, to present, his work. He received his PhD in computer science from Shanghai Jiao Tong University and honored the 2023 Shanghai Jiao Tong University Outstanding Doctoral Dissertation Awards. His research interest includes the computer architecture and high-performance computing, focusing on the software hardware co-design to accelerate the efficient AI applications. This also includes designing novel architecture and system for neural networks, particularly in the sparsity and the quantization, which is the topics he's going to present. Over the past few years, he published more than 10 papers in the top venues such as ISCA, Micron, HPC, as follows, and received the honorable mention in the 2022 IEEE Micro Topics. Okay, so it's the stage on you.
Yeah. Thank you, Professor Chen, and thank you for your kind introduction, and thanks for David organization for this meeting. And actually, it's my great honor to attend this Athena seminar serial. And welcome to my talk. Thank you very much. And actually, today I will share some our recent work about this unlocking the new opportunities in the quantitation and sparsity co-design, especially in the architecture, computer architecture for the large language model. And first, I will introduce some background, and then I will introduce some sparsity and quantization work we have done before. And the last one is a translator array. Actually, it's our newest work we published in the ISCA conference and the HPC conference. So the background. Actually, we know that the D models has earned a lot of many success in many areas. For example, you can ask your some questions in the ChatGPT on your phone, so it's successful. And so I think the background is common sense for us. And we know that the models are difficult to deploy because it has the model is getting larger and larger. For example, for the ChatGPT, for the GPT-3, and it has 170 billion parameters, and so it maybe can consume about more than 3 gigabytes storage, even the storage in the memory. So it's a very large, and we cannot directly deploy it on the GPU or even especially for the resource constrained devices such as a cell phone or the edge devices. So it's very difficult. Therefore, a lot of the research purposes, the efficient AI, actually we can also say that the tiny AI. That means that we can reduce the model size or reduce the computations for the DM models. Basically, I focus on the two main parts about for the sparsity and quantization, and we have published about more than 10 papers in the top conference, including the ISCA, HPC, Micro, and as well as also some algorithm paper in the ICRR. Actually, I think a lot of people has, I think the efficient AI has earned a lot of the attention, especially in the 2020 MIT Technology Review selected the tiny AI as one of the 10 breakthrough technology in nowadays. So first, I will introduce some efficient sparsity. We know the sparsity, actually sparsity is an old topic even in the 1990s. It's a very early stage, but in 2015, Professor Song Han proposed the first, I think the first sparsity or pruning method on the DM models. For example, for the VGG 16 models, they prune more than 90% 90% parameters, and with a high accuracy. They use some retrain or the fine tuning method to recover the accuracy for the DM models. And after that, a lot of the research has been proposed to optimize the sparsity, especially for the efficiency on the GPU, or especially how can we get a speed up or on the existing hardware on the GPU. Actually, that because that the sparsity is not efficient. It's not efficient on the existing hardware because first, that's a conclusion is proposed by actually Dr. Meng Wei and Professor Yan Chen in the 2016 because of the poor data locality. And we can have the definition for the sparsity. We call that the turning point. The turning point is that the sparsity value when the pruning method gets a performance improvement or over the dense gem. For example, if the turning point is 95%, that means when the sparsity is larger than the 95%, we can only start to get the performance. And if the sparsity is lower than the 95%, that means that we cannot get the performance improvement over the dense gem. Gem is a general matrix multiplication, so we call that the turning point for the sparsity or the pruning. And why the sparsity is inefficient? Because that we have the example about the dense weight and the sparse weight. So for the dense weight, we know that the GPU is a CMD. It's a single instruction and multiple data. So basically for the TPU is one of, I think it's kind of like a MIMD. It's multiple instructions and multiple data. So basically for the accelerators with dense, they all designed for the dense computations. They can access the memory for a bunch to access a bunch of the memory. For example, they can issue one transaction and access 4 elements simultaneously as one transaction. But however, if we are pruning some elements for the weight, and we found that the element is irregular and non-continuous, so maybe we need 5 transactions to access the 5 elements. So that means that if even we prune some elements for the weight, and then maybe improve the transactions, and we need more transactions to access the irregular weight. So actually, they need to get we need to a very extreme sparsity. So that will cause a very low accuracy for the DM models. That's why that sparsity is not efficient on the GPU. So actually, Dr. Wen Wei proposed a structured sparsity. That means we can organize the sparsity or the density or the element with some structure. For example, we can prune each row or the column, for the weight, and we can see that we can directly prune the 3 rows of the weights. That means we can directly use the original API for the quota kernel or the GPU kernel. We can just adjust the shape of the gem. For example, for the original dense matrix, we use a 4x4 weight, and we just give the API. We just give API the 1x4 shape, and we can directly use the original GPU and without any modification. It's hardware friendly. So that is a structure sparsity. However, structure, you can see that it's very regular. So that means that we cannot get a higher accuracy. That will cause a lot of the much accuracy loss for the DM models. So NVIDIA also proposed their own structure sparsity that is N2M sparsity pattern. Actually, NVIDIA published the Sparse Tensor Core A100 in 2020. They proposed a Sparse Tensor Core with a fixed 50% sparsity, and they use 2 or 4 sparsity for, as means as for the vector with size of 4. We can prune the 2 of the 4 elements in the vector, so it has a fixed sparsity. Simultaneously, and at the same time, in the micro conference in 2019, there are a paper about also called the sparse tensor core. They use some flexible sparsity with they can prune a flexible n of 16 sparsity, but it's only on the CPU simulator. The next in the next we will use a sparse tensor core to accelerate our design. So we can compare all the previous sparsity. So the first is a row or column-wise sparsity, and the second is a block-wise. Block-wise is proposed by the OpenAI, and the vector-wise is exactly the sparse tensor core, and so it needs the hardware support for the hardware support. And the final, the last one is n-wise. We call that n-wise. It's non-structured. So it's the turning point is so we can say that the row column wise the turning point is very low. It's only 5%, even close to 0. That means we can directly reduce the shape of the gem, so without any overhead for the gem computation. But for the n-wise, it has a very it's very large turning point. The turning point is very large. It's 95%. That means we prune 95% of the elements we can only achieve marginal speed up for over the dense matrix, the dense gem. So now we propose our own method to optimize the sparsity. Basically, our method is based on the gem tiling. We know that gem tiling algorithm for gem tiling is a classic algorithm for the GPU or the TPU, because we know that the GPU on chip memory is the resource is constrained. So we need to partition all the large matrix into the smaller tiles. And for each tile, we can independently run on each SM of a GPU. So it has a more fine-grained granularity, so we can implement the row or column pruning in the based on gem tiling algorithm. So we can say that it's efficient for the it's hardware friendly. It's friendly for the hardware, and we can get a high performance. And for the on the GPU, and actually for the pruning granularity is more fine-grained, so we can get a high accuracy. Therefore, we can maintain high accuracy and high performance for the pruning for the sparsity pattern. And and this work is published in the SC conference 2020. And next, we combine the sparse tensor core. We know that the tiling method is implemented on the global memory level. So we can remove the global memory access before the data is sent to the on-chip memory. So it's orthogonal to the sparse tensor core, because sparse tensor core is working on the register file level. So it's actually they are transparent for each other. So we can compare combine the tile-wise and vector-wise. Vector-wise is a sparse tensor core, and then we for example first we can prune each row of for each tile, and after that we can reorganize that into the dense matrix multiplication in the on-chip SM. And for each SM, we can continue to use tile-wise, vector-wise. It means the sparse tensor core to continue to prune the 50% element for each tile. And we can compare we call that the TVW, the tile vector-wise sparsity pattern. And this work is published in the journal TC. Sorry. And then after that, we have a lot of work to do. We need to optimize all the so actually we need to assign all the pruning for offset or the indices for all the prune the row or the column, and we need to optimize on the CUDA kernel level, but it's a very complex due to the limited time, so I will not introduce this too much. And you can refer our paper for more details about this kernel optimization. And after that, so we can find that our implementation of the TW, we implement the TW on the A100, and we can find that the turning point is only 15% for the TW. This means that we have a very low overhead for the implementation because we are the TW is very friendly to the GPU hardware based on the tiling algorithm. So compared to the OpenAI block sparsity library and the cuPlus library, we can say that the OpenAI block sparsity turning point for the 16 by 16 is 75, and for the 32 is 30%. So it's much higher than our proposed tilewise sparsity. And we also implement the catalyst on the sparse tensor core, and we know that the sparse tensor core can have the fixed, I think there's a fixed 50% sparsity. So that means that about 1.6 times speed up than the over the dense tensor core. So we also implement the tilewise sparsity on the CUDA core with IP32 precision, and we found that turning point is lower with purple size of the tiling size is 1 by 128. It's only 5% overhead for the turning point. And finally, we can compare all the sparsity pattern, and we can find that the tilewise sparsity, the TW can achieve a much lower turning point, and with an irregular distribution for the element. And on combining the vector-wise, that means we implement on TW on the sparse tensor core. You know, the sparse tensor has a fixed 15%, so is the turning point for the TVW is 50%. After the if the sparsity is larger than the 50%, we can use the TVW, and we can say that the pattern is much irregular than any other sparsity pattern. So finally, also we evaluate the accuracy on the such as BERT model. BERT model and some other CN models, and this figure is based on the BERT base and with MNRI data set, and we can find that the EW is actually obviously EW is the best because EW is irregular, but our TVW is the second best, and also TVW has a much higher speed up than the EW. So it's efficient and with a high accuracy for the D models. And it concludes that TVW can achieve about 3 times speed ups of the block-wise sparsity, which proposed by the OpenAI. And we implemented the cuSparse. We implement the block-wise with a cuSparse library, NVIDIA cuSparse library on the Tensor Core, and the TVW can has a using Tensor Core has a more than 20 times speed ups over EW. It means as a random NMOS unstructured pruning with a cuSparse library on the CUDA core. So it has so including that TW has a similar accuracy with NMOS pruning, but it has much performance than the previous work. Actually, for the sparsity. That is a trade-off between the performance and the accuracy. So, but for the condition, I think the condition is more feasible and applicable to implement on the existing hardware than the sparsity. We know the sparsity is much irregular, but the condition is regular. We can reduce the precision of the data type. For example, in the early stage, we use IP32 precision for the DM models, but we found that there's too much redundancy in the DM model, so we can reduce the precision. For example, if we quantize the IP32 into 8, we can save 4 times memory reduction and 16 time computation reduction. It's much high, so it's we can get much higher speed up than the over the P13. Also, it's more feasible because a quantization is hardware. They will quantize all the elements on the tensor, on the tensor, on the weight tensor, on the activation with a activation tensor. So it's friendly to the hardware. And however, we found that the data type, there are some data type issues because existing data type are not suitable for the DM models. They are not designed for the DM models because we know that there are 2 types of the data type. Fixed point is integer, int, and floating point is for the floating point. So we know that the fixed point is designed for the integer, and it can precisely represent all the integer for all the integers, but it has a narrow values. For example, if we have the 4-bit condition, it has only negative 15 and to the positive 15. So it has a very narrow value range and will harm, and it's not good for the DIN condition. Actually, a lot of research use floating point to quantize the DIN models, but however, DIN models, however, the floating point is not also it's not designed for the DIN models either, because they basically floating point is designed for the scientific computing. They need to represent the high precision for the smaller values. So we know that the floating point has the mantissa and the exponent. So they have the same mantissa for the large value and smaller value. For example, for the 100, they have the 4-bit mantissa, but for the 0.001, they also have they also have 4-bit mantissa. That means that we have a much higher precision for the extreme smaller values. But we know that based on the insight from pruning, we know that the smaller value is not important for the D models. So we can prune them, we can directly change them to the 0 without any accuracy loss. So smaller is not important for DM models, but we have the much higher for the smaller value. That means that the floating point and fixed point are not suitable for the DM models for the condition. Even nowadays, recently they such as Google and NVIDIA propose a new data type such as a BF16 and TF16, but fundamentally they have a different bit width with exponent and mantissa. It didn't change the character of the floating point, so they are still the floating point based condition. Therefore, and also the outlier issues. So the outlier issues for LLM is also serious because we have some experiments, and we can see that the ResNet, we use the 3 sigma rules to quantize the ResNet and BERT, and we can find that for the CM models, they have a much smaller outliers. They can also have the about 30 sigmas, but for the transformer model, they have much larger outliers. It has more than 300 sigma for the BERT models. So so also the outlier is very large. It's important for the DM models. Even 1% largest value clipping can lead to model invalid. And why the outlier is important? Because we have an example to explain that. For example, if we quantize with int4 condition, we need to quantize the negative -100 to the -8. But we can say that if we use the same scaling factor, and we will quantize all of the rest smaller values into 0. So that means a very significant information loss if we use the same scaling factor. But if we split outliers, and for the outliers, we use one scaling factor, and for the smaller values, we use another scaling factor. We can split them, and we can so we can quantize the smaller values with certain values and with slight information loss. That means so we can maintain high accuracy for the DM models. The outlier is still is also a very serious problem for the large language model. So first we propose our new data type. We call that adaptive numerical data type. We want to design a new data type which is suitable for the DM model DM condition. And we have two adaptivity for the intra-tensor and inter-tensor. And we use a matrix to measure the quantization loss. It's MSE. We know that MSE is widely used to measure quantization error. And sorry. So we use the MSE with our measurement. Actually, for the intra-tensor adaptivity, we will divide elements into multiple intervals. For example, we will divide the Gaussian distribution into I think the 4 intervals. For each interval, we use different bit lengths for the exponents and mantissa. For example, for the large values, we know the large values is important for the range. So we give all the important. That means we can intern the range for the large values, and for the smaller values, we know that the smaller values has a lot of the elements for the smaller values. So we will give a lot of mantissa to maintain the accuracy for some smaller values. So but in total, the full data type is fixed length. That means that for the different values with different magnitudes, we have a different bit length for the exponent and mantissa, but for data it's a fixed length, and we call that is flint, which combines the advantage of floating point and integer. So we can reduce MSE for the quantized tensor. And for the intertensor, we found that there are a lot of the distribution types for the models. For example, for the ResNet, for the C models, they have the image for the first layer. They have the image, so the image is like it's uniform like distribution. Actually, we know that the integer condition is uniform, so we will use the int to quantize the uniform like distribution, and also for the Gaussian like we use a flint, and for the Laplace like with a large outlier we use POT to quantize the activation tensors with a large outlier. But for the outlier, we also treat the outlier as a kind of the data type. For the outlier, we use a different data type to quantize them. Actually, this there's a independent work for the outlier victim pair design. It's published in the for the end is published in micro 2022 conference, and for the outlier design is published in the ISCA 2023. And simply, I will briefly introduce the outlier victim pair. Actually, for the 4-bit condition, we will use identifier 100 to locally distinguish the type of the pair. For example, we first pair all the elements, and for the pair, if we found that the identifier 100 in the left, and that means that the right is outlier. And if we found the pair, if we found that 100 in the right and the left is outlier, and if there are no 100 in this pair, and that means that there are no values. So for the norm values, we use an integer to quantize the norm value, and for the outlier values, we use AP4 to extend their range for the outliers. And after that, we design the ant and olive and a framework. We propose a new quantization framework, and we design the architecture, and we integrate the ant olive into existing stateful array. And but also there's a lot of the content about this design, the flint encoding design. We propose a new decoding, and we also need to design the decoding architecture and the encoding architecture, and we also need to support the type fusion, because you know, if we know that the gem has a two inputs. One input is activation, another input is weight. So if input and weight have different data type, we need to transform them into the same. I think it's transform to the same format to compute with a different data type. For example, if the input is flint and the weight is int, and we need to sorry, if the input is int and if the weight is POT is power of 2, so we directly use the digits to decode to the POT, and we decode the input into the integer, and we can use an exponent and integer to represent them, and we can use a shape and with a shifter to get the final result for the different data type with a gem. And this is our design. Also, we also designed the outlier decoder, but it's very complex. And also, you can refer to our paper for more detail about this our design for the ant and olive design. And we designed the Mac unit for the GPU, and we embed the Mac unit into GPU and sensor array. We use GPU simulator and TPU simulator to simulate our final result. That is our evaluation baseline. And this our data type and models. And finally, I want to say that this form. So we can find that based on our the adaptive data type and outlier aware condition, we found that the 4-bit PTQ is a post-training condition. It even surpassed the 6-bit result of the outlier suppression, which is the SOTA algorithm in the I think in the 2022. So it's I think it's an impressive result for the condition. That means the outlier is important for the LLM. So that is an advantage of our hardware design or the architecture design for the large language model. And the olive and condition framework pushes the limit of the LLM condition to a new state of the art. So hardware support is very important for the large language model or for the nowadays models. So actually, the overhead is very low for the GPU. We have less than 1% overhead, and for the state array, we need to 4% overhead for the state array. And finally, for the other outlier aware of the condition, like the Global, which is a famous condition for the transformer-based models, and we have a 4 times speed up and 4 times energy reduction over the Global. Including that ant and olive, it's we think that they are simple, but it's effective. Actually, we now working with some company. We want to implement on real AI chips in some. Actually, it's a big because this work is in my PhD period. So we are working on with some company in China. Actually, and win the IEEE one IEEE topics honor of mention, and all of it's participated in the Micron its conference. And next, it's our next is our new newest work. It's our recent work about a translate array, and we combine the sparsity and condition for the large language model. Now, so that is background of the GEM computation. We know that all know the GEM computation, and we found that there may be there's the matrix A multiply matrix B, and to get the matrix C. So we found that if the matrix C have some identical vectors, for example, the first row and the fifth row, and if they are same, and they will get the same result for the matrix C. But unfortunately, the probability is very, very low. It's basically 0. There is impossible for the higher precision, for example, FP16 data type to find the exactly same rows to compute remove the computation for that row. Also, we can see that the structured pruning is a special case for the similarity. That means structured pruning is prune, for example, prune the first row and the fifth row to 0. So for 0, they are the same. So I think the structured pruning is a special case for this matrix modification, for the similarity for our design. And so if we use the quantization, we can quantize the matrix to the int 3, and we found that we can the probability is much higher. It's much higher. We have a we have a high probability to find that the two rows has the same content, and we can remove or eliminate the computation for another row. And so the finally, we can find that the binary matrix multiplication is a final. I think it's a final situation for the similarity, and we can find that there are partial. We define the partial identical and fully identical. For the fully identical, we can directly reuse the result for the directly reuse the previous result. For example, we can say that the first row and the 1, 2, 3, 4, fifth row has the same, and we can directly reuse the 0.3, and we can eliminate all the computation for this row. And also, we have defined the partial identical. We can find that we can reuse a partial result of the previous row. For example, for the first row and the third row, and you can see that they have difference in the first position, and that means we can incrementally to add this corresponding element. That means there's 1.6, and we can add we can sum the 0.3 and add the 1.6 and to get the final result for the third rows. That means the partial identical, and we can eliminate a lot of the computation for the matrix for the binary matrix multiplication. Okay. So we found that the binary matrix multiplication is has a lot of the similarity or the redundancy. Actually, we implemented our idea into the SSN. We know that a spiking neural network is has naturally has a 1-0 binary activation for the spiking input. Spiking SNN has a spiking input. We can directly. So it has a inherent sparsity. It means that the bit sparsity. We can directly eliminate the 0. Skip the 0 computation. But furthermore, we can use potential sparsity. We call that the transitive sparsity, because we need to transfer the result to another to another row. For example, for the row 1 and row 4, we found that basically they have the same element in the first and the first and the last position for this row, and we multiply the same weight matrix, and we can find that if we have the row 1 result 0.2, and then we can reuse the 0.2 and to continue to add the corresponding minus 0.2 and to get the final result 0. So basically, the previous needs 5 operations, but after that we only need the 3 operations, so we can remove or eliminate a lot of the operations. We also call that the product sparsity, because it's based on the inner product for the inner product. You can see that it's inner product for the gem computation. So the transitive sparsity. Actually, we define the two pattern. The first is a partial match. That means the partial partial identical. So you can see that we can reuse the result, and we need to actual actual accumulation to get the final result. And another is an exact match. For example, for the row 5 and row 4 and row 5, they are exact same. So we can directly use for the row 5, we can directly use row 4's result, and we also define some set as S1, S2, S4. We can say that the the row 4 reuse the result of the result of the row 1, and row 5 reuse the result directly reuse all the result of the row 4. So we can save a lot of optimization. However, it's difficult to find the temporal, it has the temporal order. And we also define some prefix or the suffix. Actually, the prefix is very easy to understand. The prefix is to provide the result, and the suffix is reduce the result. So the prefix must be the subset of the suffix. So we can continue to incrementally to add the extra computation for the suffix based on the prefix. So obviously we need to find the topological order or the temporal order for the row. For example, if we so from you can see that the row 1 can reuse the row 3. So if we first execute get the row 0, I'm sorry, row 0 can get the row 0 result, we cannot reuse the row 3. So that means the row 3 must be executed before the row 1. So we have the we need to reorganize all the execution order for the row for each rows. So finally, this our final solution for that. We first we will reorder all the execution. For example, is this row and this row, and we can reuse this row, and for the row 2 and row 4 can reuse the row 2, and the last row can directly reuse the row 4's results. So we can save about 3.6 times on the spiking resonant 16. It's I think it's an impressive result about for the binary matrix modification. We can we can provide about more than 3 times speed up over the original matrix modification. So, but there is a still challenge that it's dynamic, and we know that the spiking activation is generated by dynamically on the runtime. So we also need to generate the prosperity, so the transitive prosperity on the fly. Actually, fortunately, we have a very efficient solution for the temporal or the spatial or the temporal relationship, and we can generate the temporal order for the execution. That means actually we can directly reuse we can use the number of ones for each row, and we can directly reorder the number of runs, reorder the row execution order by the number of one. For example, for the third row, they have only one value 1. So that is the first it's the first. And for the row 0, it has 2 elements, 2, 1, 0. There are 2 value 1s. So they have it's will be second execution order. So after that, based on our solution or the design, we propose the architecture. It's our overall architecture. We call it the PPU, the prosperity processing unit. So first, we need to detect all the prefix for the suffix. For example, we have the target row. We can suffix target row. The row 2 is actually here, row 2, and we need to send to the TCAM. We know that TCAM we can use the TCAM to find all the subsets. It's all the subset of the suffix row and the suffix, and we will find the most the largest subset for the that is the largest subset for the row 2, and we finally we will get only one prefix for the row 2, and that's a detector. For detector is to detect the prefix of the suffix. And after that, we can use only XOR gate to get the sparsity, and that is remove the redundant computation, and we can get, for example, for the row 2, it's a suffix is 1011, and row 5 is a prefix is 1001. So we can get the difference between the row 1 and row 2, and so we call that the prosperity or the translator sparsity. So we have a incremental to add the corresponding element for the 0010. So we can reduce a lot of the operations for the pruner. And then we will use pop count to sort the row with the number of 1, and then issue the sorted index for the processor. And finally, processor, we can for the translator array, we can find the weight, and we also load the prefix and to find the previous result and reuse the result, and to continue to get the final result for the suffix, and that's our processor. So we also provide some pipeline scheduling to make sure that we have high efficiency for the translator array. And finally, we can see that our results for the tiling, we first have the tiling design exploration. We know that for the tiling, that if we only have one row, that means that we have no similarity. We can find, and we cannot find a similarity between the one row, And also for the K, if we only have if the row size only 1, so we can also we cannot find the similarity either. Right, so that will significantly impact our efficiency. So we have an exploration for the tiling size, for the row size, and for row number and row size, and we choose a number of it's 256, and we use the number of columns. It's a row size. Row size we use 8 for the 16 for the Patel. And this is our evaluation, and it's our overall performance and energy. Finally, in overall, we outperform the GPU and all our previous accelerators, and we have the 7.4 times speed up and 8 times energy efficiency over the PDB, which published in the HPC conference in 2022. So it's I think it's also outstanding performance or the outstanding result for the sparsity, because based on our translator array. Also, we can see that after we prune all the transitive sparsity, we can find that we can have a much sparse tensor. So finally, we propose a new paradigm for the binary matrix multiplication, leverage similarity between rows and remove the redundant computation. And our purpose architecture translator array address the challenges in the translator array or the prosperity, achieve the significant or speed up of the state-of-the-art accelerators. Actually, we have some future works, and that is a direct question, that can we implement the translator array in the DM models such as the large memory? Yes, we can. Actually, actually our work has been accepted by the ISCA conference 2016, just 1 week ago. But I have not enough time. I do not have enough time to prepare the slides for the new paper, because we are preparing the camera ready for the ISCA conference. And so we can implement our translator array on the integer-based quantization. So first, how to support the higher precision quantization. We know that for the SNN, it's only has binary, it's 001 activation. But for the DM models, we have the higher precision, for example, in the 4 or in the 3 quantization. Actually, we can use bit slice. So bit slice is has been proven an effective technology in the DM models. We can use a bit slice to slice each bit for the a higher precision in integer condition. For example, for the integer 3, that is in 3 condition, we can slice the bit 1, bit 0, bit 1, bit 2, and for each sub, I think for each sub matrix for the we can split them into the binary matrix multiplication. So we can convert the DN condition to the binary matrix multiplication. Second, weight condition, and so we know that for the large language model, it's usually use a weight only condition. Fortunately, for the weight, we know that weight is static. We can process the weight offline, so we can have so we can design much more complex algorithm offline, run the algorithm offline, and for the online we can use a much efficient algorithm for the online. So we propose a new representation for the representation for the translated array, and we design much efficient algorithm. We reduce. You can see that actually for the TCAM, they have a square complexity, but we can reduce the detector or the detection into the linear complexity. So it's much efficient solution for the DM models for the weight condition, and also we can provide higher parallelism, and we can the new representation can provide another perspective. We can find that there are a lot of the parallel opportunities. For example, we can split them to multi-learns. We can split it to the learn 1, then into 4 learns. So we have a much higher parallelism, and we can use a balanced method to balance the workloads. So actually, this is a simple introduction for our work in it's a conference, but we have also a lot of the following work to do. For example, can we support the floating point? I think it's difficult. It's very hard to support the floating point. But if we can support the floating point, that means we can support the training. So now we are only focused on the inference, but after that, maybe we can transfer the translated array into the floating point, and we can support training, and it's much more. I think it's attractive for the researchers to accelerate the training process, such like the NVIP4, and we know that NVIP4 is a data type published by the NVIDIA. So can we use the advanced technology? Maybe we can use a PM to accelerate to reduce the energy. Yes, now this work we are still working on this directions for the translated array. So that's all my talks. Thanks everyone. And if you have any questions, we all also open sourced our code for the translated array. And if you have any questions, please feel free to ask. Thank you, everyone.
Any questions from the audience? You online?
Okay.
I have a general question for you. So you talked a lot about like different quantization or like these efficiency strategies. How easy or hard is it for you when you get a new architecture or a new model or something like that to run these strategies on them?
Yeah, it's a good point. It's a good question. Actually, we have explained that in our the ISCA conference. We also said that if we have for example, for the previous work and Olive, we designed a special hardware for the condition. Actually, the SOTA condition algorithm cannot support them.
Okay.
So for the translated array, we also have some advantage for the translated array because it's general. It can fit all the condition, because it's based on the integer condition. It all has it's architecture optimization. it didn't propose a new data type. So it can fit all the framework for the quantization, and this is also one of the advantage. Actually, if you design a special hardware, maybe the algorithm guy do not want to use that. They just want to use the integer or the floating points. So we need to, maybe we want to transfer our direction or our source that, oh, we need to also support the integer, but we have the we need to design the transparent to the algorithm, and under the data type, and we have some new architecture to accelerate the integer, and we do not to change the data type for the integer or the floating point. So that, I think, is a trend that our insight for that. We do not want to design some very special data type which cannot implement on the existing hardware. We also want to support the existing with a hardware improvement.
Thank you.
Yeah.
I have a question. So, for your quantization work, you mentioned some, like, for example, the overhead. The overhead, I think for TPU is like 4%. So I guess the overhead include the quantization and maybe dequantization.
Yeah.
When you multiply different data types, you get the same data type. But what are others included in the overhead?
Yeah, actually, this overhead for the TPU, it's our area overhead. It's area overhead. Yeah, we do not report the algorithm overhead for the dequantization. Actually, that's a good question about the dequantization. We know that for the such as the AWQ, AWQ has a lot of the time to dequantize and also quantize it. AWQ is only for the weight condition, because that's if AWQ cannot implement on the attention, one of the reasons is that the quantization of the AWQ is much complex, and we cannot run implement on the runtime. So it's an issue about that for the quantization and dequantization. A lot of papers has focused on to solve these problems about quantization. Also, we have this. Actually, we have another paper in this conference. We will also want to solve this problem of dequantization in the hardware support for example, for the cache level, and without the hardware support, and it's transparent to the algorithm and to improve the overall efficiency for the quantization. Yeah.
And another question is for the statistic sparsity. So you demonstrated in by using SNN. And also you mentioned in ISCA, this year's ISCA, you kind of extended to DNN.
Yeah.
How is for the DNN case, is it the speed up gain and the energy consumption gain, is it higher or lower compared to the SNN case?
Yeah, I think it's higher because the SSM, it can use a bit sparsity.
Yeah.
So that originally have the twice speed up for the SSM accelerator. But for the DN accelerator, they cannot use the bit sparsity directly. So we compare some quantize. Actually, it's my previous work, the Ant Olive. They cannot explore the bit sparsity, so we have a much higher speed up over the DN condition. Yeah.
Okay, any others?
Yeah, thank you, everyone.
If no other, the conclude our section.